Hi, my name is Masonger and today I'm going to show you how I made the temperature prediction system of the contact process. To the first glance, this video might not seem like a banger, but it is really going to be an interesting one. But why do we need it? To keep it short, we need to produce the optimum conditions for the production of sulfur trioxide and also the highest possible efficiency. To do that, we need to also provide the optimum temperature range. With that, good catalytic activity. We need also a good airflow and a good air ratio to burn sulfur and sulfur oxides, and also an absorption. The main topic of this video is the first one, the optimum temperature. The latter three are going to be covered in upcoming videos. We're going to do a quick overview on how the system works in brief, and then we are going to come back and go on with the actual temperature system. We have the whole contact process system here. So going through quickly each steps. So we have a pump and we provide air to the whole system. We have a dryer that dries the air and removes the atmospheric moisture, the water from the air. Then we have a preheater and then the air goes to the burner through a bypass valve to the dryer, and with the bypass valve is necessary here to provide surplus air to the reactors, so the catalysts can actually work and convert the SO2s into SO3, so the sulfur dioxides into sulfur trioxide. If all the air was pumped into the burner, then most of it would have been burned in terms of like oxygen, and then have like not that much air. We need like an air to sulfur dioxide ratio of like 2 to 1 actually would be preferable, to have like a surplus to oxidize it to the sulfur trioxides. We have the dryer after it. This is like necessary even if like some moisture still escaped. Also it acts as like the cooling system. The remaining sulfur dust that escapes the system will be trapped and captured here, so only the gaseous stuff can go through. Then we have the first reactor, which does the most of the job in terms of like conversion of SO2 to SO3. We have two types of measuring device. These are both thermocouplers. The first one is connected to an Arduino, and the Arduino registers and stores the data that has been read, logs it on a SD card through an SD card shield. The other one here is connected to a multimeter, and that can be hand recorded, which is kind of sucks, but this is temporary. Air, I didn't say this in the beginning, but now that I'm testing this, I'm only running through air, so the burner is actually crossed out here. Some oxygen also remaining in these. Even here probably not, but oxygen can also like be in the air. The absorber is therefore to absorb the SO3 from the gas mixture, and then the remaining gases, the SO2 that has not been captured by the absorber and the oxygen, goes through a dryer, because the absorbers always like contain some water, and some water amount will always escape these, and thus we need to dry again the solution or the gas mix. Then another reactor, then an absorber, and we do this 3 times actually. So this part, the preheater, the reactor, the 3 type of reactor, these all contain vanadium pentoxide, which needs like a working temperature of 400 to 450 C. Vanadium under 400 degrees works well in terms of efficiency, but it is uneconomical due to the low amount of conversion to SO3 from SO2. Above like 450 or 500 degrees C, the reaction kinetics actually favor the production of SO2 and oxygen too. So basically we do not do anything. So even the SO3 is converted back to SO2. So basically we have like a reverted arrow here. So we don't make SO3 from these, but actually we make the SO2 and oxygen from the SO3, even if we had some little made. To basically avoid that, we use this temperature, but we need a system to measure the temperature inside the reactor, because the outside of the reactor is significantly lower temperature than the inside. And this is why, and also because the SO3, which is hot, and also the SO2, all these compounds are really corrosive at high temperatures. So after here, I would like to use Witton tubing and not insert the probe here, because it will corrode and degrade with not even that much use. So to avoid that, I all in all will completely remove this temperature probe. To basically do that, first of all, I need to make like some sort of prediction system that with I can somewhat precisely predict the inner temperature from the outside readings. I would divide the whole design of the system into like 3 parts in total. We collected the data with the tests. Now we need to process the data. Then we need to figure out some method that is like simple enough to capture the essence and be able to somewhat precisely measure the inside temp based on the outside temp. And this is not going to be like 100% efficient and totally accurate, but it is going to still be better than just having these random outside numbers. This is necessary because if the Arduino like decides that it has like a hiccup or something like that, because it did in the past, that it started to just randomly heat it and doesn't really use the cyclical turn on turn off feature. It just for some reason just started to heat the shit out of the whole system to basically be able to avoid damaging the catalysts and the system itself. I want this and be able to predict the inside temp to avoid these kind of catastrophic failures that can happen from this. Like the system can ignite itself because there are like plastic things, and if they melt or get like hot enough, they can ignite, whatever. So to basically be and also not damage the catalyst, there will be a safety feature included in the Arduino code that will be used in terms of like this probe here will read the temperature, and then the temperature will be analyzed, and like the inside temp will be predicted based on the readings of the outside of the tubes. Then if it is like going up significantly, not normally, I mean, then the system would shut off, and then the system would basically stop itself from the destruction. So we would like to go through like a few steps, but first of all give you some clue on how it looks. So it looks more like this in real life. This is the coil that hits the 4 quartz tubes. I didn't put the vanadium catalyst, and also on basically it is on the quartz wooling that is inside these, like a bit shorter than the actual coiling, but the temperature probe, this is led into the pipe and it measures the inside temp. But as I said, the inner temp is quite like, as you can see, has these little I mean not little but like significant valleys and peaks in terms of temperature, but it shows some cyclical thing. And this, the outside temp that has been read, is like quite low deviation, has little peaks and little valleys. This is basically because the heat needs to go from the coil into the quartz tubes into the quartz wools middle where the other probe is, then through all this into the middle, which is kind of a lot of time, and also there is quite a lot of like dissipation and all this kind of transient heat transfer things happening. So it smooths out the data, and also probably adds some kind of delay in terms of like heating. So this is the first data. So have this, and wrote a MATLAB code with the help of the ChatGPT. So created like first of all graphs to basically visualize how the system works and behaves. The waiting time, the 23 and 24 seconds, these are based on the cooling temp that the relay turns on, then it go somewhere here, then there is some delay between the heat transfer and the turning on, but it turns on somewhere here, it starts to go up, turns off somewhere like here, it still goes on because of the heat delay, thermal inertia, all this stuff, and then it starts to go down, 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 turns on again, and does the same thing over and over. So the waiting time that has been basically between here and somewhere here, so this period of time is 23 on the higher graph, meaning less of a waiting time, it can cool off less and thus keep a higher temperature. The other one, 24, is more in terms of waiting time, and thus it is going to cool off more, cool the system more, and thus have a lesser temperature. There is probably some kind of error or something like around here, but as you can see, it also shows on the external temperature. I have logged all these. Now I would have needed to come up with something to basically be able to capture this, and through trial and iteration I decided that the simplest method would be just a linear regression model that takes into account the fact that there is like a different waiting time, and have polynomial fitted these graphs, got these basically these are, just going to show you, these are the temperatures, the inside temperatures based on the outside temperatures, and they can, as you can see, there are like multiple. So if we have like 255-ish outside temp, that can mean we have 470, 419, 20, 24, 25, and even 26 in terms of temperature. And thus we have like a range of 10 degrees Celsius based on like a single input of outside temperature, which is kind of like bad, but it is not that bad, because if we can imagine that this is like only a plus or minus 5 to 5.5-ish temperature deviation in terms of Celsius, then it's pretty good, because we only need to be accurate in like 50 degrees Celsius range, as you remember. So like a 400 to 450 degrees C. So we can keep it between like 420 to 450 if we find the right amount of waiting time, but probably this 23 or 22.8 or something like that would be like pretty good. And even taking into account that the actual process, this is producing us heat. In terms of enthalpy, it's 196 kilojoule per mole of sulfur. I don't know if this is like quite significant amount of heat, probably is, but what matters is that this is not going to be that much here, because I'm only working with very little amounts. So it is maybe going to increase the temperature a bit, like 20 degrees, but that's not going to be that like bad. Even if we are keeping this at like to 20 to 30, we still have like a 20 degrees of freedom, and even above that I don't think it decreases that drastically. So this is probably not the best, because it is like ChatGPT generated, but it is like between 400 and 500. So it is like here, it is like quite high, almost like 100%, and it starts to only go down after like 470-ish or something like that, 500 significantly. Work with that 5 degrees Celsius of deviation plus or minus. Also fitted this same exact model, although taking into account that this one is the 23 and this is, yes, the 24-second waiting time, and this has even like lower amount of deviation, but still kind of similar. It's like 5 till like 5.5 degrees plus or minus. So showing that the model is working quite well, even though it is like quite simple. Somewhat accurately predict the inside temp. Also will adjust the Arduino code in terms of, so the Arduino code will provide us the timestamp. so let's say it's like 437 seconds. The outside temp is like 260 degrees Celsius, and the predicted inside temp is, let's say, 415 C. I don't know, the relay is on, so 1 in terms of like, yes, it is on, so the heating is on at this second. And based on these temperature and like this and this, I will go back and manually, with like air. I didn't say this in the beginning, but now that I'm testing this, I'm only running through air, so the burner is actually crossed out here. So based on these measurings that I will do in the future, I can compare those to this and tell how much the time delay between them, so the delta t. So because probably there is some, as I said, like transient heat transfers and all this bullshit happening that are delaying the time between the actual red data and the actual real-time temperature increase inside. But that's going to be like maybe even refined with the in and on features of the relay, because then I will be able to tell like how much time has passed since the last heating, or how much time I have been heating this thing up. So we'll have like a better understanding of the maximum and the minimum temperature of the system, because it looks less kind of something like this. So I have like a better understanding on this topic. So if you've found this video valuable, make sure you like and subscribe so you don't miss out the next bangers. Thanks for watching. See you in the next one. Do that work, especially when you don't feel like it. Mwah.